came up with this idea of P-Y springs. I'll draw a few, but you can draw as many as you like. And the idea is that if this node wants to displace this way, this can oppose that by, by virtue of its stiffness. So Py curves can be chosen or derived to link the. So we can forget the soil completely and replace them with these Py springs, how many ever nodes you want, and you can prescribe what the spring characteristics are. Now, the springs should be simple linear springs. So more, I think stay no one. So the more deflection I get horizontally, the more force it generates, and it just increases linearly. Now, clearly, this would be equivalent to doing an elastic analysis. Um, Even when they proposed this recent MATLAB, and there's a subsequent version of MATLAB paper where I think it's got McClellan and somebody else, where they said the Py characteristics really should not be linear. They did some small scale, small pile test in the field scale and applied horizontal load and saw what the characteristics of the load deflection, lateral load deflection for the pile. So to match that properly, they discovered that if I'm looking for the pressure created by the soil converted into some equivalent force versus y, these will take the shape of something like this. So if I keep increasing my deflection, initially I get quite an opposition, and I'll reach some peak, and then it will flatten out. Now, one of the nice things with this PY analysis is that I can choose different springs for. So these are now nonlinear springs. So the stiffness depends on the deflection, which means you cannot solve this for any horizontal load you're applying. You cannot solve in one go. It's not a forward translating solution. You choose even higher like that. So as you go deeper, you can choose the same family of curves, but you proportionally increase their size, which makes sense because you can select the stiffness characteristics of individual springs the way you want. It's just a matter of coding it. And you, as shown here, these are now nonlinear springs, and you that's the bit which comes from the existing literature, if you like, recent MATLAB style analysis. And there are some codes which follow exactly this, and you can download them for free and use. I believe Alpine is one of them, where you can solve the uh, file response easily. So, are you familiar with this type of PY analysis before or no? Yes, some are. Yes, some are. Okay, fine. But you can say it's quite straightforward. Uh, Having a nonlinear spring gives you the complexity you need when you're handling with soil. And for various reasons, I said over the past few days, that's the critical bit. You need to get that right. And we can include the depth effect by making these curves bigger and bigger as they go deeper. So we can allow for the increased stiffness at high confining pressure. And we can also include this reaching of this plateau, which basically means you are including some kind of plasticity into the, or limiting pressure at the large displacement. There's another bit which we to do with cyclic loading, which I'm not going to cover now, but we'll come back to that later. If I forget, do ask. When we are applying the same thing for a buckling pile, what we were saying earlier is those kind of simple curves won't do. So because we know that the liquefied soil, as the pile tries to go through it, initially it does not do anything because it needs some strain on displacement. So if I'm doing the same Py, confused, I need a certain threshold displacement before the soil dilation kicks in. Yeah. So once the soil dilation kicks in, I will get a big resistance until a limit is reached, where the soil can't hold any more suction. So that's kind of represented by that, where this rate is now offset from zero, but is quite sharp. So if I join these two together, I'll get that, which is the what we're looking for. So we want a spring which is kind of stiff at the beginning, plateaus out, and then kicks up with the dilation again. And when we are applying either the buckling of the pile or pile group in this case, so we can have lots and lots of springs on each of the piles and apply the axial load and see what it does. Equally, you can do the same thing if I'm applying purely lateral load and try to do a pushover analysis of the pile group in liquefied soil. As long as I got this one, I'm in business. Either using complicated finite element code, or I can write one on MATLAB in about half an hour. Either way, they'll do the same thing. Okay. Now, yeah.
Most of the centrifuge experiments, when they have back calculated the pivot loss, they have very low initial stiffness. In your case, it's quite
Yeah, what you're saying is this bit has a bit of stiffness, right? But I can offset the curve to include that also if I want.
uh,
If it is starting, okay, what you're saying is effectively, if I understand you right, yeah,
initial.
yeah. Initially you've got low stiffness, and then yeah, that can it's just a matter of changing the curve, isn't it? So if you have the framework, choosing the curve comes straight from experimental evidence, centrifuge or otherwise. But we're trying to set up the framework. This, we ignored this part here because we're not doing laterally loaded tests. Here, we are applying axial load and let the thing kick off. And as I showed you from the data we got from the LVGT, pile buckling is an instability. Instabilities are always a runaway failure, which means I will not have that bit. In fact, it should be starting as shown there. Whereas laterally loading on a pile, centrifuge or otherwise, would require a certain amount of strain for it to mobilize its stiffness. That's the difference. Here you're kicking the thing, whereas there you're gently pushing it. The two different things. The problem is Not that we can't do those PY curves. The problem is finding the solution. So if you write a code like this and give that shape, it will never converge because it's always trying to hunt for the displacement it needs to apply to find a pressure, and it finds either the pressure is too much or too less, and it goes in circles. So convergence becomes a problem. That's true even if you run a numerical analysis. So, for example, we had a go with abacus, and we could, for ages, Jonathan Knappert could never find the answer because it just crashes after trying and trying and trying and gives up because the convergence can't be found. Then we came across this a little bit of mathematical trickery called Rick's algorithm. So Rick's algorithm is easily explained. It's not complicated. Suppose I have a lambda factor, which is effectively what I'm incrementing my axial load. The way you do buckling analysis is you apply an axial load, keep increasing the axial load until I buckle, right? That's what you do. So numerically also you do that, but in this case you multiply a given load with a load proportionality factor lambda. So vertical axis is simply what is the current axial load. Then you say, right, I'm at a position. Uh, Say I'm at that location. What I want is to follow this line, which is my instability. Once I get to negative slopes on that, that's when my solutions run away from it. A quick and easy way to solve for that is to say, right, I'm going to project this load forwards as a tangent to this. And I choose a yield surface, a bounding surface, and find where I'll go to. Clearly, that will be a overestimate. Yeah. So I should be here, but I'm here. So I'll say, right, I know I need to come down. Let me try a small decrease in my lambda factor. Then I'll come here. Then I'll say, oh, I'm still not on this surface. Let me try one more, until I'm back on this. So this kind of having a bounding surface concept will help you converge in a post-buckling runaway type situation. And this is no credit to us. This is completely done by these structures guys trying to look at post-buckling stability of columns. So we just borrowed this from that. But the concept is quite sound and easy to understand. So you don't blindly go shooting at solutions, in which case you will never find one. You will have this bounding surface as a way of containing your uh, enthusiasm. Don't just go off on tangents any which way from there. You try and control that on a particular surface. Does it make sense? Okay. This you can choose. So you choose the diameter of this, which is given by this delta L parameter. What you will find is if I choose a very large size for delta L, I'll take very long to converge. I need many steps. Whereas if I choose too small, it will converge for that step, but it will quickly crash trying to go to the next step. So you kind of choose that until it takes 5 or 6 iterations to come back to this. No more than that. And again, the way they implement it in Abacus is this thing is quite automatic. Once it has learned what the stability for your thing, it knows the unbalanced forces in the system. So it will allow you to choose delta L, which is reasonable. now we are in a position to have a numerical go at what we have been observing in the experimental results. Now, let's see if we took all the experimental evidence we have and we are now plotting on the y-axis the amplification, if you like. That is the displacement I'm going to get because of my earthquake at the pile head compared to the displacement I'm going to get because of buckling. Now clearly when the earthquake is there, it's just oscillating. So the peak of that is going to be fairly small, right? Now, when I have the, sorry, still aware, that will be my delta naught. Delta earthquake has that oscillation plus the displacement due to buckling. Okay? So once it's I have this instability driving my pile head away, my displacements are taken, and I'm normalizing that with just purely the initial displacement I get during shaping. If I do that here, so 1 means no effect of buckling. And the bigger the number, the more I ran away from my initial straight line. So that's that axis. This is the load we applied relative to Euler. Notice that there's just one experiment close to the Euler load. Everything else is under the Euler load because to apply the Euler load and make the thing stand at 60G or 80G or wherever we done, whatever G level we done, is quite difficult because we also can't make piles perfectly. So we will have our own imperfections and load misalignment even in a centrifuge. So we only ever dared go all the way to the Euler load on one experiment because it's so easy to lose the experiment if you just if you put too much load, it will buckle easily. So most of the experiments we are having are down here, where from 0.3 is obviously quite small Euler fraction, but 0.8, 0.9 is where most of the data is. So you plot the data there, and you also plot your Euler buckling equation. So there are a few close to that which follow it, and there are a few lower than that which do not follow. This blue is impossible to read, isn't it? Let me help. So these I9 set of piles, if you can, if your eyes are sharp enough, you can read it. Is short. They are short piles, and
I can read. I can read.
you can read. Good for you. But I'm worried more about. I'm always worried about people not being able to see the slides.
I can
Yeah,
read.
you won't read it.
Little effect of soil resistance and pile dominated responses.
Yeah, thank you. So what these are short piles. Therefore, they don't move very much horizontally, which means whatever the soil is there next to is not doing very much, and that makes sense. You will only demand the soil to oppose your motion if your pile wants to go away somewhere. If it's not going anywhere because it's a short pile, there's no effect, right? It's a very small contribution from the soil. So you can now plot the displacements we are getting with the axial load on the roof. And you can see whether you consider soil or just the residual, and if you include dilation, they're all coming pretty much the same. So there's not really, the soil is not working that hard, and it doesn't have to. Then we can go slightly higher up, where my Euler fraction is now about 0.7, 0.75. Now you have the big interaction between the pile and the soil. And it is a quite beneficial interaction in that the soil is able to keep this from falling over. So you got big interaction, and the pile is dominating the response. You can see this by this. This is pure no soil case, and because we have soil, we are able to reach. If I consider just the residual value, I'll get this line, and if I consider the dilation also, I'll get quite a high peak. So I can reach about 30 meganewtons. And compared to just the with no soil case where I'm only at 18, I'm nearly doubling what the pile can carry if I include my the soil contribution. Then you push it quite far away. And this is bit. This is not realistic case. Obviously, in reality, you will never design piles to be close to there being oil load. But you can see if you do that, you will need or your soil is now contributing so much to the resistance of the offered to the movement of the pile. So you need significantly extra resistance due to large strains in the while this pile soil interaction is happening, and this is mostly coming from dilation. So if I take just the resisting residual values, so this is the Euler line, and this is the residual values line. Even that is not enough. The big peak needs to come in because of the soil dilation. So in a way, the more unsafe your piles are, the more you demand of the soil and the more it will try and help you. If your piles are short and stubby, you can ignore the soil contribution and basically design them as columns, which is fairly obvious when I say it that way, but not so straightforward when we started this research. Any questions on this? So we've gone through quite a lot of little steps there. So it is possible to use the PY springs in a modified fashion using this type of double curves and add the components you want to make up the solution which fits the experimental results. And then you can look at different load conditions and pile configurations. Happy? Okay. Now we have a numerical solution and procedure. We can look at what the numerical solution tells us in terms of bending moment and where the plastic hinges should form and compare them to what actually happened. So the bending moments plotted from the numerical analysis is here. You got negative, peak positive there, peak there, and this is quite a big peak, so there should be a plastic hinge there, and here only it triggers a hinge there. So we think the hinge is somewhere here, one there, one there. So it's a 3-pin mechanism that's allowed to form here. So this is obviously not as dramatic as the one I showed with 3 pins, but it's kind of neat that you can go back and get the bending moments to see the location of hinge formation or expected hinge formation from the pure structural point of view based on our analysis and compare with what actually happened. This one is abacus with, yeah. But not in the true 3D way. Because we only have beam elements and springs, abacus also can solve this quite easily. The only reason we have to use abacus is because of the Excel algorithm. It's already coded in. Okay? So, we come to the summary of this. What have we learned? So, pile instability can occur when the soil surrounding the piles liquefies. Absolutely straightforward. Also, it's fairly straightforward to make a quick check, and this is what we recommend as practicing engineers people should do, is run your, it takes you about half an hour to do a simple Euler type calculation or even Perry Robertson calculation. These things have been published out there for a long, long time. So please estimate your eccentricity, load eccentricity, or pile imperfection. Get your eta factor, do a calculation, and see. Make sure you're not putting on these piles loads even coming closer to buckle. Okay, and that's an easy check to do, and we can stop many of these from liquefying, buckling when the soil liquefies. It is possible, if you're more researchy minded, that you can track the pile buckling in the post buckling period because uh, A, it could be fun, and B, you may be able to see what extra, if you're doing the ultimate ULS type calculations, ultimate limit state calculations, you want to know how far you can push your files. If you're doing that, this is a quite good way of uh, making progress. So there are lessons there for simple engineering calculations as well as for some sophistication if you want to. It's about, yeah, so that's the, my plan was to come in. So what time do we stop for lunch? Huh? Okay, 12:30. Okay, 12:30 we will aim for. I'll start at 12 again. So we got about 15 minutes now before I start the next bit. If you want to ask me any questions on this part, morning part. Yeah.
So what if there is any non-liquefiable layer sandwich between two liquefiable layers? In that case, how the pile will change?
So where are you talking about the non-liquefiable layer? At the top?
No, so in middle, as a sandwich between two liquefiable layers.
You're talking about, so that is a liquefiable layer. And your file is going through that. I would expect that, okay, there are a few checks you need to do. A little bit we'll talk about this in the afternoon, but what is the resistance I can get here? Okay, if you can get enough resistance, then you probably take your effective length as, so this probably will do a shape like that, and this one has to buckle like that. You know, it's like having a strut between two, a column that is supported by a strut in the middle, which is the typical structural solution to stop buckling. One good thing is that the force that is needed to stop this from buckling is not that big. So you don't actually need that soil to be all that strong. It needs to not liquefy and stay there. Because if you did this like a pure structural analysis with a strut, the force in the strut is fairly small. Yeah.
Um, Instead of springs, we go for the constitutive model of the soil, like using raw sand or something like that.
Yeah, I mean, you can do that, but then you're talking about fully, uh, you're then going into the realms of FE.
Do they simulate that strain hardening behavior of soil
Yeah,
during
you
that
can do that.
reconstruction.
Yeah, exactly. I mean, that's what I'm saying. If we want to run this whole thing as a 3D flak analysis, for example, you should be able to pick this up. In fact, a lot of Iranian papers I was talking about earlier had a go at trying to simulate buckling with flak 3D. Of course, you can. Nobody said you can't. It's just uh, once you know what's going on, it's not a problem. Especially if somebody else has already coded into the flag 3D, North Sand, PM3 Sand, whatever the constituent model is. Of course, you can do it. You will get the same behavior. I'm pretty sure. The tricky bit is not that. The tricky bit is actually to know it's a problem. Because,
Mechanism needs to be understood.
yes, that is complete. All my lectures end the same way. If you understand the mechanism, then it helps you in terms of analysis, it helps you in terms of planning the experiments in the first place, and, and in finding solutions. And no two engineers will have the same uh, answer or the same way to stop it. But we are all engineers, so we are always solving problems which do not have unique solutions, except in your exams.
So when we are considering the same problem of liquefiable soil and we consider two pile groups with different configuration and different spacing, will this have different effect on these two?
Yeah, all the sorry, probably haven't explained enough. Uh, sorry, all the different file groups I was showing there, I9, I5, they had different configurations. So we were trying to push each of them according to their own Euler configuration, right? So yeah, each will have an effect, but they were all showing the same behavior.
So can we expect a pile group with smaller spacing to be more stiffer than that of one with a larger spacing?
I'm tempted to say not as much as you think. If you imagine that the pile groups are, say, closely spaced, the reason you're thinking that, oh, the closely spaced ones can't buckle so much because they tend to act together, that's only true if these piles are all trying to buckle inwards, where the soil is getting trapped. But if you worked with concrete and the reinforcement in concrete, especially if you visit post-earthquake damaged columns, you will see that they're all splaying out because it's always easy for the bars to kick out than kick in, right? That's why you have these shear links in that. So you should, yeah, don't be just a geotechnical engineer. Keep your structures with you. It's always helpful. And that's why, whether the piles are spaced closely or further apart, you may not get as much benefit because they all can splay out as easily as one another. So the pile spacing should be less of an issue. It will help when you come to spreading. I'll come to that later. But good question. I like that. What do you think about the problem? Yeah. Anything else?
So,
Yeah.
so the funder put after the report that you have written, in that they were said that most of the large diameter piles are performed than the smaller diameter.
Yeah.
How do you distinguish it? It's a large diameter pile.
Usually your LOD ratio. I think we did one calculation yesterday to call them short pulse, long pulse, flexible or rigid. That all comes from effective length over diameter. So if that is, you can have some LOD less than 5 beats, short, and LOD greater than 10 beats long, that kind of thing. So that's of course not considering the soil effects in it, but normally you would expect piles like what recent MATLAB have tested are half a diameter diameter piles, so they are fairly flexible. If you have a 1 meter diameter pile, a pile with steel what do you call, chasing outside, those will be quite have much higher buckling loads, and the problem will disappear. There was a question somewhere behind that. Somebody wanted to ask something, or you're all happy? So now we want to translate slightly from looking at both the axial behavior but also lateral behavior because of mostly the lateral spreading problem. I've given you examples of that before, and I'll probably show some more later on. But if I have a pile group which is carrying all the load, the last thing it wants is some big lateral load being applied at the same time. And that makes the problem much worse, both from buckling point of view, but also from a the whole stability point of view. Because it's like saying in our Perry Robertson curves I was showing you earlier, it's like adding a big eccentricity to the load. And the more eccentricity I have, the lower is my Euler buckling load. So that is the issue. So we want to move more into this application of looking at axial behavior, but in the presence of lateral loads. So if I were to think about this, you got pile groups. First factor you probably want to think about is this embedment. Now, a lot of work I've shown you, the piles are just at the surface. But usually in practice, you probably would embed the pile cap a little bit into the ground, right? So that's one embedment effect you want to consider. Spacing, as you were saying earlier, especially for lateral loaded piles with lateral spreading happening. Dense spacing is important. Obviously, if the piles are tightly packed, but what's the minimum spacing you would probably design a pile group for? Huh? 2.5. What's the largest spacing you'll probably design for? 3. 2.5 to 3 is very small. 2.5 diameter, pile diameters, and the largest spacing is about 5, I would say, about 5 diameters. Probably extreme, but not certainly more than 5 diameters. So the spacing we should consider. The other issue is how deep should these piles embedded into the non-liquefiable layer for you to mobilize enough fixity. Now, unlike the single pile, now you've got a group of piles. So it is possible to get more rotational fixity by having more of them, especially if they can go deep. Now, this is quite critical, especially if you are in a country where the contractors are constantly claiming pile refusal as the limiting factor to stop piling deep. Because you often end up in not having sufficient depth into competent ground because it's easy for them to walk off and say, well, that's the point. The refusal occurred. That's the one word they learn, and you are none the wiser. So you've got file spacing effect, if embedment effect, and you also have whether the files are stiff or flexible. Of course, that should always play a role. Before lunch, I'm only going to go back and talk about axial behavior, and then we'll come back and look at the lateral aspects as well. But one point I wanted to impress is we talked about pile buckling, right? Now, the real research question you're going to ask is if I have a pile, that's my say fiber layer, and so loose sand or silt, and this is dense sand. Okay? What we haven't considered is if I have my normal vertical load, is it easy for the pile to buckle or to settle into the slab? And there is some evidence and reason for this. What we know is even in dense sand has dense 90%, 85% relative density, you will get significant pore pressure buildup. Okay? So from a pore pressure point of view, loose sand produces positive pore pressure, dense sand also produces positive pore pressure. Okay? There's one main difference in which they both are apart. You can say tell them apart. One is what the loose sand does in this high pore pressure environment when it's liquefied. The dense sand tends to dilate much more strongly when you shear it compared to loose sand. Now, that's the background knowledge we have. But the real question is, if I have a real long stick poking through the soil and I'm trying to push on the top of it, is it easy for it to settle or is it easy to buckle? And that's a genuinely difficult question to answer, and it's not necessary any of us know the answer to. It's a six of one and half a dozen of other, right? So you can't tell whether the settlement is dominant or so. The question really we're asking is, will the pile settle or will it buckle? There are a few simple things like what we did in all the tests I showed you. We rock socketed them. Effectively, the piles were fixed at the base. So if I have the same situation where I drill a hole and make sure my pile is well and truly rock socketed, then of course we are only leaving an option for this. Yeah? There's nothing else the pile can do. It can buckle or it can stay vertically up. But if you ask your practicing colleagues, how many piles in the world, or at least in India, are rock socketed? Get a percentage. It's about 5%, maybe 10% if you push it. Because often the pile lengths you need don't reach the bedrock. So, although we made a lot of noise about buckling and looked at all the complications, in practice, either I need quite a long length into dense sand to make. So, what we're saying is to get buckling, delta vertical at tilt should be 0. So the vertical displacement of the pile tip must be zero. Only then it can buckle. So either this can be achieved either by rock socketing, which we can all imagine, or I have such a long pile in dense sand that it can't settle anymore. So those are the only two cases you can think of where either piles are too long, or too or into the rocks when buckling should be a real concern. For all other cases, maybe it's easy for the pile to settle. Does that make sense? So this is the important condition you got to bear in mind. Once we recognized this, we said, let's have a go with looking at vertically loaded files which are in dense sand. Can we ever get them to buckle? And then we realized that actually we don't understand how the pile group and the pile cap share loads. So we know when we have driven the piles into the ground and made our pile cap and applied the load vertically, what happens? You got bit of base capacity, you got shaft capacity, and you have some pile cap capacity. So if I add all these three together, my vertical equilibrium equation says that should match up the applied load, or should be more than the applied load to give me a factor of 8. That bit is dead clear. What's not clear, sorry, there's another point. Structural engineers, quite rightly, don't believe us about this pile cap capacity. They said the soil is too shallow. You guys may work out your silly bearing capacity calculations. We'll ignore that and we'll consider that's an additional factor of safety. So whenever you design pile caps, I'm not talking about pile ramps, only pile caps. The pile cap capacity is almost always ignored worldwide. It's not just us. Everywhere in the world, they ignore that. And say, yeah, that gives us some extra capacity which adds to our factor of safety. Okay, so that is the static situation of design before you start. Then imagine we have the earthquake, we liquefy that down. Pore pressures go up, effective stress comes down, we know all that. And we link loss of capacity of the piles to loss of effective stress, which is what the pore pressure is doing. And therefore that was cause some settlement. But in terms of the load sharing, no idea. And this is what we discovered when we started thinking about it. There's nobody else who looked at this who tell us, what's going on to this base capacity, what's happening to the shaft capacity, what happened to the pile cap capacity. So that's a big question mark. We don't know. And what we know, of course, is post-earthquake, this situation must be same as that. So you'll have consolidation, soil will come back, and it's there, it gains its strength, and your effective stress goes up as the pore pressures dissipate, you have increasing capacity. So we know long term will be having the same or similar setup as this. Not same because the soil has reorganized itself, but from an equilibrium point of view, it should be true. So we set about trying to understand what happens in between. So I'll tell you part of the story now and part after lunch. For this, to study this problem, we had to do some unusual things. Like normally when you're doing these tests, you gauge your files to measure bending. Whereas for this, we had to gauge them to measure axial load because we want to know what's happening to the shaft capacity during the earthquake loading. So we created this pile group which has 1, 2, 3, 4, 5 locations at which they're full bridge gauges, and I think we gauge two piles. It's a 2 by 2 pile group with front and rear piles gauged. And we also put some load cells to measure the axial load at different locations. And of course, we can measure pile settlement easily, accelerations easily. One other thing we did was to put pore pressure at the transducer inside the pile to measure what is the pore pressure at the tip of the pile. So these are fairly heavily instrumented piles. Costed me an arm and a leg, you can tell me. But the Mark Stringer was a good student, and I knew he would do a good job. So, the first set of tests we did were to do with all the piles standing free of the surface. So, we have loose sand, dense sand, and the piles going into the dense sand, and the pile cap is clear of the surface. So there's no question of any pile cap capacity here. Basically, we've done what the designers are already considering, took the soil away. So there's no doubt. So that is the first set of series of tests we did. And, okay, you do the earthquake, we applied a fairly large earthquake, 0.2 G, shaken it for quite a lot of cycles. And these are the loads measured at the top and bottom strain gauges. These are measuring vertical loads, right? So you can see that they're getting up to about 500 kilometers, about 50 tons in prototype scale in each one. So these are quite a lot of load, as I said. The other thing we could do is what was happening with the in the post-earthquake period. Because here, what's important is that during shaking you got big pore pressure buildup, but we want to see what's happening post-earthquake. Are they coming back or not? So as the pore pressure dissipates, we started looking at the load cells and see whether the pile loads are coming back or not. So you can see that these are picking up the loads in the post-earthquake period, which is good. That means that you are coming back to your pre-earthquake state reasonably comfortably. And this loss, this change in load sharing is mostly happening because you lost all your shaft capacity. So you could see from the instrumented piles that while the load is changing at the strain gauge level A and E, as shown here. So I showed you 5 levels, A, B, C, D, E of strain gauging. So we could see how at each location the load is changing, right? So based on that, you can work out how much is your shaft capacity and how much is your base capacity. Oh, sorry, not capacity, wrong word. How much is your shaft load and how much is your base load in the part. So we can separate the components out. If you do that, and then plot that with the pore pressure, you can see what's going on in each case, right? So as with different time or different levels of pore pressure, you can see my shaft capacity going to the shaft capacity going to 0, and the base capacity is also, so yeah, I need to tell you where I started and where I end up. So I start here and end up there. Start here, go down, and end up there. So eventually we lose the whole thing because the pile wants to settle. As the pile settles, nobody can help you. There's no shaft. You haven't got base or shaft capacity to support you. That's why it's not in equilibrium. I'll show this and then we'll stop. This was a side story. I'll come to the main story later on, but this is a slightly side story in that one of the uh, points I need to make clear is when we are doing these experiments, you fire many earthquakes. So you fire first earthquake, get some measurements, increase the size of the earthquake, apply a stronger earthquake and a stronger earthquake like that. So we were a bit worried that we're destroying the soil too much in each of these earthquakes. In other words, will it be very different if we did a fresh centrifuge test on each of the on separate models and applied these earthquakes separately? So that's slightly how would I say this? It's slightly besides the point from what we are trying to learn here. However, it's important from a scientific consistency point of view. It's no good doing all these tests and showing results if fundamentally applying the uh, bigger and bigger earthquakes on the same soil model is going to change your results significantly. There will be some change, but are they changing significantly? Part of the problem is PhD students. If I ask them to do 5 or 10 centrifuge tests, they're happy to do that. If we ask them to do 50, they'll run away. So we won't have any students. It's important that we get this right. So we are looking here at the pile cap settlements for a small earthquake and a large earthquake. So we're starting from the earthquake time point of view when they started, and but this earthquake blue one was applied after the effects of earthquake one are finished. So the core pressure buildup, they dissipate, and then we apply the second earthquake. So if you can see, so we have that as a much slower rate of settlement compared to this one, right? Because it's a much bigger earthquake. Then you see, Mark Schlinger got a very bright idea. Why are we plotting like this? Why won't we put one on top of the other? So we plotted that. Okay. So if you then uh, so I misread the label before somebody picks up. So the blue is the earthquake one, uh, green is the second earthquake. So the rate of settlement in the second earthquake was smaller than the first one. Okay. So if I plot my second earthquake, not starting at zero, but where this fellow ended, isn't it remarkable that the soil remembered exactly what it was doing in the first earthquake and continued exactly along the same route? I mean, if I didn't tell you that these are two separate events, superpose them together, it's almost it remembered, the last earthquake happened some 10 days ago. I remember what stress state I got into, and now this new earthquake came, therefore I must respond with this stiffness. And if ever you needed proof that this method of applying multiple earthquakes means that you're continuing the same stress state and no big damage has been done, this graph proves it. So uh, it's very, very critical for research validity point of view. And it's genuinely surprising how well they fit. Okay. I'm contemplating whether we should stop or do this bit and then stop. Hungry, not so hungry? Go? Okay, right. So the next set of tests we did were with the pile cap in contact with the surface, which is more like the field case. When we say they are in contact, they're always a little bit embedded. We push them until they come into contact. As you G up, they will undergo some settlement. So they're always embedded by a few millimeters. Few millimeters times G level. So it's like quarter of a meter or half a meter embedment. into the ground. So we said, right, let's try these. Very similar experiment, very similar locations of instruments and the rest of it. And now I want to compare the axial loads in the freestanding pile group and the pile cap in contact. Okay. Now you can see on the left hand side, those are the things I've shown you earlier, where you're going up to 500, 600 kilonewtons. Compare those to the ones on the right. First thing you will observe is they're very different. Surely you can't call the accelerations of 0.2 g-ish, but look at the behavior of what the loads in the piles are doing. They're completely different, right? So these are more or less oscillating. Started there, oscillate, and end up somewhere there, oscillate, end up there. These things are dropping down all the way to zero, and then going up again. And this is very, very interesting. All we have done that's different between the two tests is pile cap free of the surface, pile cap resting on the surface. That's all there, the difference is. Why is the behavior so different? And for this, you need to not just look at the top, and here we're only looking at the tip and at the head. Strain gauge A and strain gauge E. B, C, D we ignore, right? But we have the data for that. So why don't we plot the axial distribution of load with depth for both cases? And this is amazing. If I look at the freestanding piles, one is when we started, that is before the earthquake began. So you got some distribution of the axial loads with the depth. Obviously, you would expect as the skin friction picks up, your axial load in the pile comes down as you go towards the tip. More or less. So that kind of thing is happening. Then you shake the soil, you look at it, it's come down to 0.2, where all the loads are dropped to 200. So from 400, roughly, it's dropped to 200 kilonewtons. And then you come to 3, which is maybe 5 seconds after the earthquake, 10 seconds after the earthquake, and so on. So 5 is long time after the earthquake. So this kind of loop suggests that the load distribution starts there, goes there, and comes back again as the core pressures dissipate. The key question is, why is 200 seems to be the minimum it can get to when all the soil lost its stiffness? Can you think of a reason? It can't go lower than that? The clue is Isaac Newton. And equilibrium. As I explained, this is a pile group which is freestanding pile, right? Pile cap. What we are saying is on these loads, we're measuring strains or axial loads at different locations here. You still have V. So even if this is trying to settle into the ground, somebody must be carrying V. Who is going to carry V? This guy can't do anything. He's clear of the soil. These are the only ones that they can do. So equilibrium demands and Newton demands that this applied V is shared between the four piles, and the lowest they can do is to have V over 4, which is 200 kilonewtons. So there's a good reason why that does not go lower than 200. Now the second bit makes sense. The second one is doing that. Okay? Now, if I apply V and each is carrying V over 4, what this experimental result show is your axial distribution starts more or less at 400 like the other pile, and then they go all the way to 0 and then come back up again while you are reconsolidating. That means what's the difference between these two? This guy, right? So now he's in contact with the pile cap, which means if the pile group wants to settle in, he'll say, no, I'm going to give you my pile capacity, pile cap capacity. So briefly, while the thing is trying, it's all turned into soup, you know, due to liquefaction, the only person who's helping you is the person who you ignored as part of your factor of safety calculations in the static design. Imagine you don't have the cap, you'll be getting stuck with that one. So the pile cap capacity ignored worldwide is the one thing that is saving these pile. If not for that, more buildings would have collapsed in all the past earthquakes. It's just that we don't know. And not only we don't know, we deliberately ignored it. So you can see why we need more research into understanding how the piles, pile cap, and the pile shaft, pile base, and pile cap, how they share loads in different loading scenarios. This, if ever you needed proof, you can quote this paper. This is all the proof you need. It's perfect. It follows equilibrium. It follows exactly what you expect from simple calculations, nothing complicated, and shows you what's going on. Okay? So, my colleague and friend, Malcolm Bolton, came up with this idea. Now you see, now you don't. He calls it. You know, magicians use this word all the time. So they show you something and then it disappears and they say, you see nothing, right? Now you see, now you don't. So basically piles do that to us. So before the earthquake happened, they're all there, supporting your structure. When the liquefaction happens, they disappear. You don't see them. And post liquefaction, post consolidation, they come back. So this is what we call now you see, now you don't trick. Piles are pulling on us. And the only saving grace is the poor, ignominious pile cap, saving the day. Isn't it wonderful that you can make some important observations like this? And if you say this is pure research, not useful for practitioners, I don't know what is. This is exactly the kind of thing practitioners can't do on their own, but we need to tell them in a way they understand. And now you will say that pile cap design will be considered a bit more seriously. So we're saying structurally, the connection between piles and pile cap should be good. Otherwise, we will mobilize those hinges we talked about. We're talking about cap capacity must be considered properly, must be properly designed. If you can even lightly compact the soil for a meter or 2 meters below the pile cap, how much benefit would you get? No, I haven't. I don't need to do all those experiments to say, look, you can improve this here. Then I'll be a Japanese researcher. I'm not going to do that. Okay. Once you have the idea that this is what's going on, you can do all kinds of things to improve your capacity and stop even make the settlements even smaller. You're good engineers, so you can do that. But what you need is that clarity of thought of what component of the file design is acting well and how does it rescue the situation. Okay? Right. I think with that bright spot, we'll stop there and continue the rest of the story when we come back. Any questions on this part?
Cyclic.
So-
Cyclic.
Yeah, I mean, you can, uh, because we have the cyclic variations, you could plot how the axial capacities are oscillating as well. And in fact, we also have four pressures next to it. So we can do a lot more with that if somebody has the time. I'm kind of, we need to revisit some of these tests again. There's so much more data there. But from liquefaction point of view, the cyclic loads are really only variations in the mean over the mean load. So yes, they are 10-20% change on the axial load, but that's not going to change the overall behavior. It might be interesting from soil mechanics point of view why we are getting a 10% change and link it to the stress state of the soil on either side of the pipe, but that's just for us. Yeah, but from a design point of view, people don't care. And I don't think the piles are designed so closely that 10-20% changes in axial load are going to get. As I said, you've got factors associated of about 1.5 on structural strength. Yeah.
After liquefaction, during the consolidation phase, will the soil exert a downward pull
Yes,
on the pipe?
it does.
And
You
then-
can, did I stop it? I'll show you. Yeah, it does do down drag. As it pre-consolidates, it drags on the piles and our things record that as well. And again, that's another topic people are talking more of now, that liquefaction induced down drag during reconciliation. But only thing we need to know is how much settlement. The issue of down drag stresses on piles due to consolidation of clay is very well established. So we know the mechanics of that. There is this zero plane concept which we can use, and yeah, and a lot of research has been done on that already. So all we need to know is how much will be the settlement from my liquefied soil. If I know that, I can pull all that existing knowledge and apply. Yeah.
So in the experimental setup you have shown us, in the experimental setup, so you have connected the piles and the pile caps. So what is the type of connection assumed there, whether it is a partial fixity condition or a full fixity condition?
You're clearly an experimentalist. Thank you. Yeah. No, no. The way these piles were designed is so that we can use the same pile in different pile groups. So there's a nut and bolt arrangement on the top. So you kind of make sure that when you tighten the nuts, you get absolute fixity on the pile. So you can, more than structural, real structural designs, we can be very assured. Also remember, we are calibrating them by applying low axial loads and bending loads on them. So although the piles are gauged to measure axially, you try to apply a bit of bending just to make sure that you gauge the wire properly and it's not picking up any cross coupling between bending and axial load. So you need to be careful. So you don't make a single calibration factor, you make a matrix by applying three directional loads. Good point. Yeah, you must be absolutely sure that they're fixed, and these were designed for that purpose. Any more questions? Okay, in that case, we will take a break now, and we We'll go when your bus is ready. Yeah,
Yes, we'll check that.
I need a break.